Okay, Soul of Science. Fantastic book. Came out in 1994. I read it once then and probably once in between, and then read it again for this time, and it's really wonderful. Jeffrey called it
I just thought you should turn that so they could see better.
turn the,
Yeah, turn that a little bit.
Is that better?
That's better.
Stand to the right. Okay. Jeffrey called it a intellectual feast, and it is, but it's a kind of a conceptual argument which goes from the beginning through the end, and so it's hard to leave parts out. So it's very difficult to decide what can we short circuit a little bit to keep it from being 2 hours long. But anyway, written by two people, Nancy Pearcey, who many of you know is a Christian author. She's been involved with a lot of books, written books with Chuck Colson and other people. Wrote a book on feminism, wrote a book on, and one of my favorites is this one here, which is Total Truth. All truth is God's truth. and Charles Thaxton, who got a PhD in chemistry and then did graduate work at Harvard in history of science. And so we're in two good people's hands. I've actually had the good fortune of meeting both of them. Charles actually lives here in the Atlanta area, though he's getting on in years a bit. But he was a co-author of a book called The Mystery of Life's Origins, right? Which is one of the first real books on origin of life from a perspective of someone who had a foot in the intelligent design camp, although that was very new at the time. And he's listed first, and it's not in alphabetical order, so he must have had a major part in that. But it's a relatively bad book. So we've got some good people writing some good material. So on the books, let me share over here. This is the really dangerous part. Look at that, Paul. Thank you for coming this evening, ladies and gentlemen. All right, now, in preparing for this talk, I felt I owed my audience a clear definition of what constituted the soul of science, since that's what it's about. To address that, let me introduce, let me get rid of some of these here. Come on, up like that. I'll get rid of them altogether for that matter. I don't care.
Bruce, can they hear you? Ask them. You're talking.
Can y'all hear me? Hello?
Well, for us too, speak up.
Yeah.
Yes.
Yeah. Okay. All right. Good. I'm a little coarse. To address that, let me introduce to you a philosopher who you've never heard of. He's so unheard of on the internet, they don't have a picture of him. His name was E.A. Burt. He wrote in the 20s. He wrote in religion and science and stuff like that. Very educated man. His PhD thesis was called the metaphysical foundations of the modern sciences. It's actually influenced quite a few people, and I learned about it by reading about intelligent design and things of that nature. And one thing he said in there, which is endeared him forever, is this. Well, it's not that. This was working before. Well, that's going to be a problem. Let's see. Let's try one more thing here. So, okay, well, there it is. So you can read it like that. If you don't do your metaphysics first, your methodology will become your metaphysics. Now, that needs a little bit of unpacking. The first question is, what is metaphysics? And there's a shortcut. I think it would help if we agree that the worldview could be used in place of metaphysics. Could be substituted for it, which would give us something like, if you don't pay attention to constructing your worldview, your methodology will become your worldview. We could even potentially use the word religion. If you don't pay attention to, you don't construct your religion, we don't pay attention to knowing what your religion is, your methodology will become your religion. But religion brings a bunch of baggage with it that we don't want to deal with. So let's stick with metaphysics. To define metaphysics, let's look at an authoritative source, none other than the Physical Foundations for a Christian Worldview by William Lane Craig and J.P. Moreland. And in it, you will find a major chapter devoted to metaphysics. Look at that. it's a Diwali miracle. We've actually celebrated lots of Diwalis living overseas, Festival of Lights, right? And there's a chapter called on metaphysics. And I looked at it, I love the very first opening. Metaphysics has a public relations problem. When some people hear the word, they are likely to think of a certain area of the bookstore at the mall where you get books on the New Age movement, astral projection, and Eastern herbal cooking. Right? Others are likely to think of metaphysics as purely intellectual speculations about a subject when science cannot give us an answer to our questions about that subject. However, popular, neither of these is accurate. Right? They go on to note that metaphysics has a long and distinguished history, boasting some of the greatest thinkers of all time. Early creeds of Christianity was full of metaphysical terms like person and essence and substance and subsistence. But what is Craig and Moreland's definition as follows? This won't help. It is difficult, if not impossible, to come up with an adequate definition of metaphysics.
Yeah.
Usually it is characterized as a philosophical study of the nature of being or reality and the ultimate categories and kinds of things that are real. Think about that for a second. The philosophical study of the nature of being, that's a big thing, or reality, that's a big thing, and the ultimate categories of things that are real. Could there be a broader definition of something? Right? And within that broad category comes one very important question, the need to decide on the status of material versus immaterial things. The question being whether the latter, the immaterial things, are to be deemed part of reality. As a good Christian, we must simply come down on the side of the existence of immaterial things. Think God, angels, demons, but closer to home, free will, consciousness, goodness, trust, faith, the list is lengthy. So what Bert is saying is if you are a scientist who has not adequately done his metaphysics, and of course few have, then whatever methodology you select through which you pursue your life's work will become your metaphysics. It will, for example, dictate to you what is real and what is not real. If you are a materialist and select only material things as the subject of your research, you will likely conclude that immaterial things do not exist. After all, your methodology, to which you have outsourced your metaphysical questions, will demand that answer, and it may just tell you that free will doesn't exist because it has no physical evidence. So what has all this to do with the soul of science? First, it is defensible to suggest that the soul of science is in fact metaphysics. And second, if that is true for modern science, I see no reason why it should not be true for earlier scientific eras. And indeed, we're about to meet scientists operating with very different metaphysical ideas, and we will find them interpreting or framing their discoveries in concert with their metaphysical beliefs. This is the thrust of soul of science. Pearcey and Thaxton look at the history of science to determine just what this interaction has looked like and what we can learn from it. And we will see these interactions alive and well in all areas of science, right up to today's challenges from quantum physics. So with that under our belts, let's turn more specifically to our book. Here are some helpful guides. Here's a table of contents. It consists of 4 chapters, 10 chapters in 4 parts. We will handle chapters 1 and 2 together as they are short. Part 2 introduces the first major period of scientific revolution up to the Enlightenment. Part 3 introduces the important role of mathematics as science attempts to better ground its findings in something that can be identified as truth. This is a very interesting aspect of our journey. It involves the collapse of an idol. And then part 4 looks at the modern scientific revolution with relativity, quantum physics, and ends with the relatively recent developments in biology. I will end with an epilogue that hopefully will capitalize on all that we have discussed and will give us food for thought and discussion about some very broad and important questions. Your outline, you'll find, is divided into chapters, but each chapter is numbered from 1 to whatever number we needed for that chapter. I'll try to keep you posted as we go. If we're in chapter 4, I say we're at 3.2.1. That's 3.241 in chapter 4. Okay, so if you're following along, I don't think you'll have too much time keeping up with that. So as we said in the world, let's do this. That's the end of the slides. Each chapter begins with an AI summary, right? Which I'm going to read with you. It's right there. It's at the top of your chapter 1 and 2 together, right? This chapter lays out the book's central thesis. The authors argued that the scientific revolution did not happen by chance and was not an emancipation from religion. Instead, it emerged in Christianized Western Europe because the Judeo-Christian worldview provided the necessary intellectual and philosophical soil. This worldview included key beliefs such as rational and orderly God, who created a contingent, non-divine, and real physical world that humans could investigate. The authors contrast this with the other worldviews, such as are found in some Eastern religions or Greek philosophy, which they argue did not provide the same impetus for systematic scientific inquiry. And then chapter 2, they examine the historiography of science itself. How has the history of science been portrayed? They discuss how the positivist view of science, which was the one which is still around today, but and was reigning until the beginning of the 20th, almost the middle of the 20th century, which sees it as a linear progression of pure facts divorced from any philosophical but religious context, has been challenged by more recent historical scholarship. They advocate for a new historicism that recognizes the influence of extra scientific factors, including religious and philosophical ideas, on the development of science. The chapter sets up the framework for the book, which we will explore, and we will explore how these worldviews have shaped scientific thought. So we're in chapter 1 and 2, point 1. The Christian worldview that our summary is referencing contributed many important things to the creation of science as we know it. Nature is real. Unless it seems too obvious, there are philosophies and religious traditions that treat the world as unreal. God made it good. We see this explicitly stated in Genesis right at the creation, every day, in fact, right? By contrast, the ancient world often equated the material world with evil and disorder. Nature, while good, is not God. Pagan religions, typically animistic or pantheistic, treat the world as either the abode of God or an emanation of his essence. This de-deification by Christianity to drain the deistic nature out of reality, right, was critical to the foundation of science. God is rational, and hence the world is orderly. If we did not believe this, who would bother to carry out an experiment? Because I do experiment today, and then tomorrow I try it again, I get a different result, right? We would never do science. And we have perhaps the most important, we have the rational capability to explore and explain the natural world, to grasp and unfold its intelligibility. This has never been a deliverable of atheism, only from theism, and particularly Christianity. And while these deliverables from Christian theism give science good motivation, histories of science, starting with the Enlightenment, told a somewhat twisted story. This is point 2 in chapter 1 and 2. From the Enlightenment up to the earliest 20th century, scholars generally divided history into 3 stages. The ancient world, regarded as brilliant, though limited in its scientific understanding. Then the medieval world, dismissed as a time of intellect and cultural desolation, also known when I grew up as the Dark Ages. And the modern age heralded as a time, ta-da, when reason and enlightenment arose to dispel the myths of medieval superstition. A grand story. It's been told over and over and over again. 2.1, this approach derived from positivism, a philosophical approach to knowledge that ultimately tried to make the claim that truth was in fact only available through science. It held the main seat at the table until the middle of the 20th century, promoting those scientists in the past who thought like we do today and dismissing those who had different opinions. A classic of this genre is Andrew Dixon White's 1896 2-volume tome, A History of the Warfare of Science and Theology, which despite significantly declining factual support, was still being studied well into the 20th century. Did a lot of damage. Right? But by the mid-20th century, things began to change with the arrival of a new approach to the history of science. Instead of comparing people from the past, from their past with our present, supposedly more sophisticated beliefs, why not try to understand them as people of their time? Right? What they classified as good science defensible, given the beliefs and level of knowledge available at that time? This was called the idealist school and is well represented in science writing today. One major result is that the so-called Dark Ages has disappeared. We now call it the medieval period, right? As we understand better the advances that were being made in those centuries, not to mention the founding of numbers of great universities. And finally, at 3.1, and that is the approach taken by our authors. As you might guess, we will consider the metaphysics on offer that scientists in history would have encountered and look at how that has been reflected in their work. This is seldom cut and dried, but is always formative. Right? Chapter 3, AI. This chapter delves into the 3 main philosophical traditions that influence early modern science: Aristotelianism, Neoplatonism, which you probably have never heard much about, and materialism. The authors explain how each worldview and with its distinct assumptions about nature, the nature of reality, God, and humanity shaped the scientific work of the time. They show that debates among Christians over these different approaches to nature were what drove much of the progress in science, not a conflict between science and religion. By the way, any questions from chapters 1 and 2? Clarifications? We have a little liquid here.
I was just gonna comment on the reliable, orderly God, that, in Proverbs, it talks about vinegar on soda. As if you could always expect vinegar on soda to do this, to have this chemical reaction.
Right, orderly.
Through the centuries.
Through the centuries,
Everybody reads that.
Another important point is that the people in those days were reasoning from God to rationality in nature. They weren't looking at the rationality of nature and assuming that it was a characteristic of God. This was a gift of God, literally. Okay, so the chapter 3. The earliest metaphysical system with a scientific perspective was Aristotelianism. Aristotle lived from 384 to 382 BC. He was a philosopher and a contributor to many fields of knowledge. His worldview pictured the world as a vast organism, in part because he was fascinated by biology. As a result, his insights into most things drew from that biological influence. So 3.1, Aristotle concluded that all forms of motion or change, all natural processes, we would say, are directed by a built-in goal or purpose, the so-called final cause, which he also called an object's form. To do it the form and encapsulate it within a concise, logical definition constituted for Aristotle scientific knowledge. When I first read this some years ago, I thought, how simplistic. What do you mean a ball has an internal direction? A ball has something in it that makes it roll downhill, or whatever the thing will be. But I note, as I shall today, that in biology, certainly we are still debating purpose, right, to this very day. The second major metaphysical system of interest to us was Neoplatonism. And as a little aside, several of us in here know Richard Howe. He's a professor emeritus of philosophy and apologetics at Southern Evangelical Seminary and a good supporter and friend of the Areopagus. And I sometime mentioned to Richard something about Neoplatonism. He said, do me a favor. He said, as soon as you figure out what it is, I want to be the first to know. So don't expect this to be cut and dried, right? If Richard Howe didn't know, right? I skipped a thing. No, we'll be good. Plato, of course, preceded Aristotle, but his writings first came to be well known in the West through the mystical religion developed by Plotinus called Neoplatonism, or just New Platonism, and by other people as well in the 3rd century AD. But it kept changing because different generations of people would add this or change definitions or what have you. Right? Plotinus taught a blend of Greek thought melded into a unified philosophy that centered on the ideas of animism and panpsychism. Unless this seems too arcane, Isaac Newton was influenced by Neoplatonism. So we're doing this for a reason. Right? These terms usually mean that things, in this case, everything, has a life or a soul. The world was made up of passive matter and a world soul animating and directing natural processes. Its appeal was not to rational forms like Aristotle, but rather to the creative power of spiritual forces, often thought of as divine, though not transcendent or personal. Right? So some people thought of it as divine, other people didn't think of it as divine. Neoplatonism influenced 2 distinct streams of thought, astronomy and medicine/early chemistry. For example, in astronomy, we find that Neoplatonism had a mystical respect for the sun. For example, so where Aristotle taught that the Earth was the center of the universe, Neoplatonism taught that the position should be given to the sun. This mystical view of the sun appears to have influenced Copernicus to form his heliocentric proposal, what we now know as the solar system. Up to the 16th century, the only people who wholeheartedly accepted heliocentrism were themselves Neoplatonists. It came from their metaphysics. Right? Not only Copernicus, but none other than Johannes Kepler, who really did until later people came along. He developed the first elliptical orbits and got us out of the circular orbits and made a lot of changes and made some wonderful. But he was a very occult sort of guy, was influenced by Neoplatonism. He apparently was attracted to the idea of the sun as being God's seat, or at least his power, and hence the center of the solar system was the only suitable place. Here's a summary of Neoplatonism, 2.5. In summary, Neoplatonism exerted an enormous influence upon the intellectual world of the 16th and 17th centuries, had great appeal for those who revolted against the arid rationalism of Aristotelianism, not unlike the appeal Romanticism 2 centuries later had for those who were voted against the arid materialism of the Enlightenment. Everybody's got their, somebody comes after you, says whatever your philosophy was arid. The third of our three great medical systems is the world as machine, alternatively called materialism or mechanism. Despite their differences, Aristotelian and Neoplatonism both saw the world as an organism. There was something living about it, and a lot of debate centered around how God acts in the world, and then in later centuries, whether God even exists. Scientists working within the mechanistic tradition were struck by the regularity, permanence, and predictability of the universe. God was seen as the great engineer who had created the universe as a giant clock, whereas Neoplatonists regarded nature as an interplay between passive matter and active spiritual forces. Mechanistic philosophy rejected the latter, regarding nature as purely passive. The laws of motion were imposed on nature from outside God. And so if Aristotelianism portrayed God as the great logician and Neoplatonism as the great magus or magician, then mechanistic philosophy portrayed him as the great mechanical engineer. In later centuries, mechanistic philosophy would be used in polemics against belief in God, especially after the Enlightenment. And most of its initial supporters were Christian. What impels natural processes is not any inherent purposes of forms, as Aristotle would have said, nor any inherent active forces, which is, as Neoplatonists would say, but God alone. That, of course, was the view of the early mechanists, of which Galileo was one of the first. He took a belligerently hostile stance toward both Aristotelianism and Neoplatonism, rejecting Aristotle's final causes and the Neoplatonist attraction to sun mysticism and panpsychism. Panpsychism means everything's got a little bit of psyche in it, a little mental activity. He saw God as a divine draftsman and architect who created the world as an intricate mechanism, following the propositions of geometry and arithmetic. His dispute with the church is now known to have been over his rejection of Aristotelianism rather than his support for Copernicanism. As in Galileo's time, the church had just been through the Counter-Reformation, and they had doubled down on Aristotelianism and the whole view of Aristotle and how the world works. So when Galileo came and said, we got to do away with all that stuff, they weren't happy. 3-4. And then we have the conflicting case of Isaac Newton, 1642 to 1727. At first glance, Newton was seen to be the ultimate mechanist, right? That's the clockwork universe. And his work does give support to that, including his rejection of the Neoplatonic concept of the world soul. But looking more deeply, we find conflicting forces at work. He too wanted to defend the realm of spirit against the encroachers of mechanistic philosophy. To do this, he made peace with the Neoplatonic idea of active forces, and in fact revived the work of Kepler, who was a Neoplatonist, which had fallen into not being known, which had been accompanied by a great deal of Neoplatonistic speculations. When Newton's Principia was first published, I find it fascinating. The mechanists dismissed it as just another expression of the mystical philosophy they were trying so hard to expunge from science. They were convinced that the idea of gravity being a force that had its effect across long distances with no physical contact was fanciful, far too close to the Neoplatonist idea that the sun exerts an occult power of attraction over the planets. It took Voltaire's adoption of Newton's idea for Newton to be viewed positively on the continent, but in that process, Voltaire and other Enlightenment philosophers scrubbed his work to remove any non-mechanistic ideas. And this mechanist interpretation is the typical picture of Newton and his work that comes down to us today. He was also a believing Christian. He had his own issues. He had some issues with the Trinity and so forth and so on. He wrote a lot about religion. He wrote more about religion than he did about science, actually. 3.5. Let's conclude this chapter with some general thoughts on how we might judge rationality. It had been assumed that the idea of a scientist's rationality should be focused primarily, if not exclusively, on his beliefs themselves. And if today the only acceptable position is mechanistic, then any interaction of a scientist in the past with earlier and now demoted systems would taint the scientific result. But were we to define rationality as that which follows logically from a given set of assumptions, then it should be quite rational to say, for example, that a Neoplatonist would search for numerical harmonies in nature. They had a lot of Pythagoreanism and mathematics in Neoplatonism. Or for a Christian to seek to know God better through examination of his creation. Today, most historians realize that fundamental decisions within science are often influenced by extra scientific commitments. 3.7. The fact that a researcher considered scientifically interesting in the first place the kind of research he undertakes, the hypotheses he is willing to entertain, the way he interprets his results, and the extrapolation he draws to other fields, all depend upon prior conceptions of what the world is like, hence his metaphysics, her metaphysics. Each philosophical tradition inspired particular kinds of research and supplied an interpretive framework for understanding the results. To take these ideas a step further, consider these quotes. 3.8, opposition to new theory is not necessarily due to stupidity, fear, or blind dogmatism. In most cases, it is due to disagreement over the philosophical and religious context in which the new theory appears and which is being used to support. The three categories outlined in this chapter help to make sense of the varied streams of thought influencing science in its nascent period, that means basically up to the Enlightenment. Each intellectual tradition inspired the formation of concepts and motivated discoveries of enduring value to science, and as we shall see in the following chapters, they've continued to exercise an enduring influence on science up to contemporary times. We're about to see some more evidence of that, this controversy revolving around the question of how God interacts with the world. I guess the takeaway from this point is there was a lot of stuff going on in the metaphysical side, right? And there were lots of influences flowing back and forth. And never was science standing by itself, just doing its work, measuring its things in the lab with no intention of this, because everybody's metaphysical position, whether they had generated that or not, or even thought about it or not, was also guiding them into the kind of things they wanted to investigate, the way they interpreted their results, the kind of questions they asked, what they thought these findings meant. It was a very mixed bag, right? Questions, comments?
Yeah.
We got a voice I can borrow? Yes, go ahead.
Going back to Newton, generally critiqued as more of a theist than a Christian.
Yeah.
So how would you see that differentiation expressed in his scientific theory?
I'll have to get back to that.
Yeah,
I could talk aimlessly for 5 minutes, but that wouldn't help us. I could talk aimlessly for 5 minutes, but that wouldn't help. I almost brought a little biography of Newton. There's a guy by the name of Mitch. I don't remember his name now. He's a apologist. He lives up in Idaho somewhere, and he writes some wonderful books. The Atheist Who Didn't Understand Himself, or something, or How Not to Be an Atheist. And then he wrote biographies of Galileo and Newton, and they're fascinating. And I've read that for a while. But I guess typically, if you're a theist, I don't know. I guess a theist believes in a transcendent God, but is it personal? Right. I think that's a big that's a big issue.
Yeah, I just didn't know if you picked up on any implications of that.
No. All right. Chapter 5, the belated revolution of biology. This chapter turns to the history of biology. The authors explain why a scientific revolution in biology lagged behind that of physics. They discuss how early biological thought was heavily influenced by Aristotelian ideas of purpose. Again, there's that word. Greek, it's teleology, purpose. And how that transition to a more mechanistic view of life was a slow and controversial process marked by ongoing debates about the nature of living organisms and their relationships to God. Biology did turn to metaphysics, but in this case, it was to Aristotelianism. You got your choice, there's lots of metaphysics out there. You can pick your metaphysics. This viewpoint from 700 years before Christ took its biology very seriously, even though it was taxonomic, meaning concerned with classification rather than with experimentation. The revolutions we've been speaking of up to this point apply mainly to physics and astronomy. Chemistry was typically associated with medicine and biology, and both relate to the party. By the late 18th and 19th century, biology had blossomed forth into a welter of contrary approaches. Think what was happening. The Western empires were putting themselves together, the English and Spanish and the French, and they were sending boats out around the world. Cook was circumnavigating the world. They would put naturalists on there and scientists on there, and their job was to collect as many specimens of beetles and plants and so forth as they could. These were flooding back into England and France and Spain, and they just had this welter of stuff. And so suddenly, we got to figure out how to classify this stuff. Anybody got an idea? Well, this is Greek guy who had some idea back in 300 BC. Ultimately, it was to Aristotelianism that the biological science turned, the major determining factor being that biological issues simply cry out to be explained in terms of purpose, because we think of purpose as being something that a person has, right? That a human being has, a will, right, to have a purpose in life. which was present in both Aristotelian and Neoplatonism, but only Aristotelianism saw the world strongly in terms of organism, and to that biology ultimately turned. And we're still talking about it. The whole intelligent design issue was about can we find a kind of purpose which can't have arisen by chance, right? But from some kind of intelligent activity. In chapter 5, 1.1.1, Aristotelians tended toward the descriptive side of biology. They interpreted the order in the organic world as an expression of the divine plan of creation. Their reasoning was the logic of categorizations. Their method was observations of the world. We talked about this a little bit on Sunday in the Sunday morning class. One highlight of the territory we are overflying is the arrival of Darwinism. Of all the things, and Jeffrey mentioned this on Sunday, of all the things that he kicked off, perhaps the more influential was the denial of purpose. Purpose, you will recall, was a key to both Aristotelianism and Neoplatonism. And so for anyone sympathetic to Darwinism, these two fell out of favor in exchange for a mechanistic view. Many contemporary scholars will confirm that this was a feature of Darwin's theory and not a bug. Purpose had long been associated with God in different ways, but without it, only mechanism was left standing in the lists. 1.2.1 in chapter 5. In short, Darwin eliminated his intellectual competitors not only by arguing negatively against their position, but also by offering a positive alternative in his own terms. His style of intellectual attack was to portray his opponent's theories not merely as competing scientific explanations, but as interlopers that had no business being in the same ring at all. 1.2.2, though Darwin's view of nature was mechanistic, it was quite different from the mechanistic philosophy of classical physics. In earlier centuries, scientists had seen no conflict between a mechanistic picture of nature and belief in God. But with Darwin, the machine became self-generating, self-operating. Nature was conceived not as a finished machine, but as an unfinished process, a mechanistic process indeed, for one generating its own power, eliminating the need for an external engineer or creator. One final Darwin quote. By the end of the 19th century, mechanistic philosophy had become radically materialistic and reductionist. That reductionist means you go from biology is physics, it's chemistry, and there's physics, and all down to, they knew about atomic physics, taking everything down to the lowest kind, as if the more you knew about the lower levels, the more you knew about the whole thing, which I think is a fallacy all by itself, but that's right. But as we transition to the 20th century with the discovery of DNA, the idea of purpose was given new life. This was, in some senses, exactly what Aristotle would have expected, that organisms, and indeed all things, have a purpose which is interior to them. In many cases, this is exactly what the genetic program of the modern biologist claims. Think of an acorn growing into an oak tree with no outside help, right? It just does it. All three of our systems had their adherents, both today, although, of course, the received wisdom in our era always falls first in the mechanistic camp. But the argument about the existence or non-existence of purpose continues to be a major point of contention. And then if you agree that purpose exists, the question becomes, how does it arise in material and biological things? Is it from God? How does he interact with the world? I find myself wondering if perhaps Charlie Kirk has learned the answer. So when we talk about the modern world, it's a very modern one. I'm mistaken with one of the top atheists. When Anthony Flew died, he kind of became the major academic atheist in the country. In 2008 or something like that, he wrote a book called Mind and Cosmos. And the subtitle is Why the Materialist Neo-Darwinian Conception of Nature is Almost Certainly False. And he was excoriated by his fellow academic atheists. I mentioned today, not Saturday Review, one of the weeklies, had a cartoon on the front that's this guy being burnt at the stake and all these hooded academics in their capuchin, sort of pointing mug going around shaking. What do they call it? Anyway, this burn, and that was the way it was. But he was saying Darwinism isn't even going to capture the physical life, much less our values, anything above that, right? And so the point was we need something that's almost like we need to find an atom. It's called purpose, that we can put into our mechanistic thing, But he's right there, but he just won't make the step over to theism. He's got to say, we need to find some middle ground between this non-theistic stuff and this theistic stuff. So we can maintain.
Do you know, did he ever follow up on that book?
I don't know. Probably it's like, I have no idea.
Because he's looking for a third way.
Yeah.
So you don't have to believe in God.
I have a presentation on that,
Not
but I haven't read it in a long time, so I don't know what it said. Compared him and Planting and Phaser and a couple of other people, on this issue. It was called Good News in the Battle Against Atheistic Naturalism. That was the name of the presentation. Anyway, part 3, chapter 6. I love this. I hope you will too. Math in the Past, Discovering the Structure of Creation. The book explores the historical understanding of mathematics. Before the 19th century, many scientists and philosophers saw mathematics as a means of discovering the very structure of God's creation. They believed that the laws of mathematics were not human inventions, but were instead reflections of the divine mind, and that by studying them, they were thinking God's thoughts after him. This view gave mathematics a high degree of dignity and authority. Right? This is a very important chapter, but the AI summary, while good, does not adequately reflect the importance of the relationship between mathematics and science. As you will see, it made major changes to then current scientists' view of truth and how we obtain it. And as we will see in the next chapter, set them up for a significant disillusionment, something for which we are in some ways still recovering as a civilization. Point 1, early thinkers saw the value of mathematics, but at the same time saw that truth was typically the product of deductive reasoning. Deductive reasoning started with either self-evident facts, as known by the human mind, or physical facts discerned by the senses, taken from the environment. And when these are combined and modified correctly by deductive reasoning, they will arrive at truth. That's my text message. It does get your attention, though. There's a reason for that, but we'll go into that. It's called the axiomatic method. And in 1.2, in the 4th century, Euclid had shown that geometry, one of the more important fields of practical mathematics, how do you measure a pyramid, built of whatever, surveyed land, could be structured from a limited set of self-evident facts called axioms, and that by deductive reasoning, all the theorems of geometry could be derived from them. Systematized in this way, geometry came to be regarded as the highest form of mathematical knowledge. For nearly 2,000 years, Euclid's work was held in the highest regard as a guide to what was true. But there are inherent dangers here. You may not know that Copernicus's views of heliocentrism, or you may know, I may not, relied primarily on the fact that the mathematics needed to calculate the position of heavenly bodies under his idea were mathematically simpler if the sun were at the center of the solar system. There was, in fact, very little empirical evidence, and Copernicus himself was a rather tepid scientist. But 84 anomalies, when you calculated the planet, they were always saying, this one, but here you have to change it by this, and when this happens over here, you have to change it by that. And like 84 of these things that you had to do to keep track of the planets. But if you put in heliocentrism, there were only 34, right? What's wrong with that? Well, our friend E.A. Burt, who we met briefly at the beginning, who still haven't seen a picture of, thought there was plenty wrong with this, right? Is the universe fundamentally mathematical in structure? And you're kind of assuming that. Can we devise theories about nature based on mathematical calculations alone? Is it proper to choose one theory over another just because it is simpler mathematically? You can guess that Burt probably said probably not, or you better think really carefully about it if you want to go down that path. But what is clear is that acceptance of the Copernican theory also marked the acceptance of a new worldview, a conviction that whatever is mathematically true is true in reality as well. And this set mankind to mathematics as the only unshakable knowledge. But here the plot thickens considerably. Remember that we were discussing where to put purpose in our various views of the world, but now the idea arose that mathematical laws might be the driving force of all reality. This was a completely novel concept of causality. 2.1, if mathematical laws cause physical phenomena, then it seems to follow that these phenomena are as certain and necessary as the mathematical laws themselves. To speak of the laws of nature as necessary is to suggest that the same relationship exists between physical objects or events as between two sides of a mathematical equation. As physical phenomena came to be seen as certainties driven by mathematics, God came to seem unnecessary to explain the design in the world. Right? There's always that trade-off between these things. If any of you are feeling that there's more than a bit of hubris here, you're very welcome to your thoughts, right? The search for certainty represented the secularization of a religious concept of truth that had guided man for millennia. 2.2.2, as belief in God declined, the axiomatic method modeled on the geometrical reasoning replaced God as the guarantor of human knowledge. But there soon appeared an epistemological flaw in the way of thinking. You always get Greek words with me. Epistemology is the branch of philosophy that deals with how do we know something is true. If you want to add something to your store of wisdom and you got a candidate, you got to apply your epistemological investigation to see, am I warranted to believe that this is true? I can put it in my kit of things that I believe are true. Recall that epistemology studies how we arrive at knowledge, and the flaw was to evaluate anything, we had to use our minds. Whether you're a rationalist, someone who starts from thinking in the head, or an empiricist, somebody who starts by looking at nature and seeing and getting sense data, whether you're either one of those, you had to use your mind to discover first principles and then to interweave them deductively into new truths. So unless we consider our minds to be infallible, how could we ever know anything? Could we even apply the rules of epistemology successfully? And here's a quote that's not in your outline. What then is the status of all those vivid colors, sounds, smells, and feelings we normally experience? Well, if they are no longer properties of objects themselves, they must reside in the mind of the person perceiving the objects. Galileo called them secondary qualities and explained them as interactions between the objects and the human mind. What do you mean by this? The secondary qualities are sometimes known by the name qualia, Q-U-A-L-I-A, qualia. And one interesting thing about them is that they are what make the world so wonderful. Imagine not being able to enjoy art or music or food. The hardcore mechanists would tell us that we are only reading the signals we are getting from these objects, sometimes in the form of light, sometimes in the form of sound, even touch, but that simply can't be true. If I step over to the piano and play a chord, you can probably tell me whether it's dissonant or pleasant. If I play this one, you don't have any problem with that. So what is it about the sound coming out of this piano which tells you that that chord is harmonic or dissonant? Nothing. All those notes have perfectly good places in all sorts of chords and pieces, chromatic scales, and all sorts. And by the way, if you had someone come into you from a different culture like Arabia, they might find that second chord be really, really neat. You know, they work in a quarter tone scale, and a lot of things that we find, So where does this judgment come from? How about the hearer's mind? Am I making a point? This can be expanded to all the qualia we mentioned. The light from the landscape scene does not indicate in itself that it is beautiful or ugly. Placid lake, snow-capped mountains. And by the way, here's part of the signal that says, oh, by the way, this is a really pretty picture, right? The taste of a dish from a master chef may be entrancing to one and disgusting to another. Need I go on? Could it be that what makes life enjoyable is something we manufacture in our own minds? Think of that for a while. Right? In short, the world of science describes becomes totally different from the picture the mind actually sees. And you should be thinking about Thomas Howard, right? Chance of the Dance, saying that the modern world has flattened the world. I leaned on the stand, Jeffrey. He warned me about that.
Stuff out the deck.
Yeah, but because we've drained the world of all of its really interesting components because most of them are generated in our heads. A great chasm opened between the world as it supposedly is in itself and the world the mind perceives it. This then is the modern crisis of epistemology. If the human mind in its normal operation is so misleading, how can it be trusted at all? In conclusion to this chapter, in earlier years, scientists had believed that God made the world and then our minds so that we could understand it. But with the dwindling of belief in God, this connection, this sponsorship and guarantee of a reliable connection between reality and our minds was broken. The seeds of doubt were planted in the emerging modern mind that would soon flower into outright skepticism, as we shall see in our next chapter. Questions, comments? Time to breathe.
A lot of information.
Yes, that's why the outline is 17 pages, 12, 13 pages. Yes.
It's kind of analogous to like words morality come from, like, pleasant sounds, pleasant taste, pleasant sights. I'm thinking about intangible versus tangible.
I think it primarily comes from our interpretation of the physical world. not the emotional or because morality has no, well, I mean, there's an act which we choose to be immoral. I suppose it could work that way. But these are usually talking about physical things, which normally we'd expect the light to tell us, or whatever it is, however we see them, or experience, or hear them, or feel them, or whatever, we expect to tell us something about it. But it is another thing. I think a lot of that doesn't mean it hasn't been instigated by a God who gave us instructions as to how to do this, right? But you need to do this too because you need to be discerning, right? That's the whole purpose of it. Don't be misled by false philosophy. Okay, chapter 7, the idol falls. This chapter recounts the development of non-Euclidean geometry in the 19th century. The discovery that there could be consistent geometric systems other than Euclid's shattered the idea that mathematics was an absolute and apodictic, meaning clearly established or beyond dispute, source of truth about the physical world. This event led to a profound shift in the philosophy of mathematics, with many mathematicians coming to view their discipline not as a discovery of reality, but as a game of internal consistency, a system of human-created rules. And it also ultimately mathematics divided into applied and pure. My Pam's brother John has a math PhD from Stanford, and he said the mathematicians, the pure mathematicians, nothing annoys them more than something that they discover or invent, and the pure side is found to have a practical use. It's just terrible. 7.1. We ended the last chapter noting that the seeds of doubt were shortly to flower into outright skepticism. This started with concerns about the human mind, but continued into the Scottish Enlightenment with the philosopher David Hume. Hume aimed his comments at the axiomatic method. This method required that relationships, especially causation, in reality be necessary ones. But this annoyed Hume. I think that was a very low bar. Hume always seemed to be annoyed. He proposed that no matter how we winnow through our sense perceptions, we find nothing of causation. What we find, if anything, is correlation. And many before him had said correlation is not causation. Hence, said Hume, we're talking about things that appear in the human mind only, right? Hence, said Hume, the idea of a causal connection has its origin in human psychology rather than in some perceived form of physical necessity. You make it up. You identify something as causation. Mathematics for Hume was tautological, meaning that most of it was only drawing out the implications implicit in its axioms, in the way that someone might announce that a bachelor is an unmarried man. There's only one piece of information there. At the end of the statement, we know no more than we do when he said bachelor. Right? So Hume, 1.1.1, Hume pulled mathematics down from its pedestal as the supreme science, reducing it to a collection of formal definitions, which are mere tautologies. Hume apparently stirred the philosopher Immanuel Kant, 1724 to 1804, from what he called his dogmatic slumbers, as Kant put it later. It seemed clear to Kant that Hume was wrong, but how to preserve a role for the mind other than noting correlations? 2.1. Kant answered Hume by postulating that the mind itself creates order. That's what we're sort of nosing around that idea, which we then mistakenly regard as existing in the external world. With this move, mathematical proofs ended up being subjective, not having any relationship with the outside world. It is sometimes said that Kant was a second Copernican revolution, but instead of placing the sun at the center of the planets, he placed the human mind. 1.2.2. So Kant saved human knowledge, but only by giving up the world. In his epistemology, human knowledge is absolute and necessary, but it reveals nothing about the outside world. It was a pretty steep price to pay to solve a problem of epistemology. Kant's view of mathematics as tautology was bad enough, but Euclid was about to fall from its perch as the preeminent science. We're having a bad century here. 2.1, of all the axioms and postulates that underlay Euclid's geometry, all seem self-evident except one. The two parallel lines never meet. It may seem obvious to all the empiricists out there, it was not something known from observation. After all, who has seen to the potential end of two parallel lines? Especially given the fact that they could, in theory, go on to infinity. Not to get too geeky on you, my notes say, why stop now? There are two ways to test the parallel axiom. Assume that there are no parallel lines through a particular point above or below a line, or assume that there are many parallel lines through it. But as mathematicians played with these supposedly falsifying assumptions, expecting their inclusion into geometry to lead to the dead end of contradiction, that did not happen. It began to dawn on them that what they were discovering were new systems of geometry. The further it goes, the worse it gets, right? To jump to the conclusion, mathematicians today believe that any form of geometry is potentially applicable to some type of physical space. Riemannian geometry, in which parallel lines converge, is applicable to geometry on a globe. Well, think about the lines of longitude. At the equator, they look like they're parallel. By the time they get to the top, they diverge. There's something called Lobachevskian geometry, in which parallel lines diverge, but it only works on a surface which, if you think of a herald's trumpet, the little thing goes out and bell. So here's small, and it comes to bell, and they'll put the bells together, and that shape, parallel lines diverge. If there was something of that shape that meant anything to us, right? So the chasm between what was mathematically true and what is true of our physical world began to crumble, right? We couldn't rely on that anymore. There ensued debate after debate about how to ground mathematics, if not in the physical world. What's the status of negative numbers? What about irrational numbers, which cannot be expressed as the ratio between two integers? How about calculus, which made use, indeed hinged on infinitely small quantities, but failed, at that time at least, to offer any explanation of exactly what they were? Right? A lot of people thought calculus was going to just collapse of its own weight because it didn't have a definition of a number line which you could do calculus with. 2.2, for some time, mathematicians soldiered on, relying on a shadow of a belief in God, that things would work out in the end. The foundations movement was started to try to rigorously axiomatize all branches of math. Significant progress was made until the advent of set theory. Let's look for a time like the Holy Grail that would save mathematics until it too displayed certain problems. It has to do with self-referential statements, which typically cannot, by their definition, be true. 2.1, take the sentence, all rules have exceptions. But as a rule itself, it must have an exception. Otherwise, it would be a rule with no exception. But then the original statement would be false. Makes your head spin. Many of these attempts founded on the work of Kurt Gödel, 1906 to 1779. Some of you may remember Gödel, Escher, Bach. It's actually about Gödel, I think, in German. It was a book in the 60s. It demonstrated that within any system of significant complexity, like algebra or geometry or something like that, it is possible to find a sentence like, this sentence is not provable, which is like our example above of all rules have exceptions. This brought down most of the attempts to axiomatize all the mathematics. Gödel worked at an institute at Princeton where Einstein took up residence. They used to take long walks together. Some conversations. You might want to consider the following quote from the book on this point. Mathematicians, 3.1, continue to develop mathematics and to search for laws of nature, but with a crucial difference. They no longer believe they were discovering the design of God, but only the work of man. And the subjectivity and limitations that always beset the work of man now came to be seen as unavoidable in all fields of human endeavor. We're never going to get this right. We've been working on it now for, 2 millennia. We're still treading water, right? Which leaves us once again with a pressing question. Why does math work? Today it's divided into pure and applied, I mentioned before. The pure side only addresses problems inherent in mathematics itself. The applied only with real-world issues looking for a kind of empirical support for their work. But if Newton said force equals mass times acceleration, F equals ma, you divide both sides by a, you get mass equals acceleration, or right, force equals mass acceleration. Divided both by a, you get mass equals force divided by acceleration. Why should that work? I mean, you went into your study, you discovered that force equals mass times acceleration. You went into your study, you better think, and then you played around with it, and you were not expected to find this to be true in the real world. And it is. Right? There's something going on here. The question is, what? It's what philosophers of mathematics do with things like that. Doesn't pay well, but they do it. This then is the dilemma of contemporary mathematical philosophy. The amazing fit of mathematical concepts with the physical world cries out for explanation. Without the assumption of divine creation by a reasonable God, there is no explanation. Mathematicians must act on sheer faith, the faith that lacks any basis. So a question for me, does it seem to you that our desire to view the world objectively is being frustrated at every turn as more and more things are thrust into the world of subjectivity, which by definition means the human mind? Questions? Do we need a stand-up break? Are we okay? Okay. I'm gonna get simple now, we're just a relativity. Is everything relative? Revolution in physics. The authors discuss the impact of relativity theory, primarily Einstein's work. They explain how Einstein's theories challenge the certainties of Newtonian physics and how this in turn fueled a broader cultural relativism. They caution against the incorrect and common assumption that because physical laws were found to be relative to the observer's frame of reference, that moral and religious truth must also be relative. But of course, a lot of people grabbed onto this and said, that's exactly what this means. I've got freedom now, I can do anything, right? Relatively, like the upcoming chapter on quantum physics, is a difficult but extremely important topic. It's not really my intent to explain it. Make it less menacing might be a better, more attainable objective, right? Pull at least one fang out, right? But first, let's distinguish between special and general relativity, both foundational theories developed by Einstein. Special was published in 1905 as 1.1, deals with the relationship between space and time for objects moving in a straight line at a constant velocity, meaning not accelerating. Its main principles are the laws of physics are the same for all observers in uniform motion, but if you're not in uniform motion, all bets are off, right? General relativity, which was published in 1915, is a more comprehensive theory that incorporates gravity. It redefines gravity not as a force, but as a curvature of space-time caused by mass and energy. This curvature dictates the path of objects, including light, which is why the planets orbit the sun and light bends around massive stars. Special relativity, some key ideas. This is the only one I'm going to go into in any depth at all, because kind of a central feature of Einstein's theory was to make, this is 2.1, make time and space relative, meaning that it was relative to the observer's position. That is so-called his or her frame of reference. Let's stand at the train station and look into a car. Scott, can you hear me? Can you hear me? Okay.
We can hear you now.
My apologies. Somehow the power cable got pulled out of my computer and everything went dark here. Not in the room, but just on the screen. So they needed a break, believe me. All right. So we're going to go back out and share the screen again.
Okay.
Well, actually, you know what? I'm not going to share the screen. Nothing new is coming up on sharing the screen. We'll just leave this up here. I'll leave it up here. We can see you guys. Okay. All right. So, making time and space relative. Where was I? You're standing on a platform. There's a train in front of you, but it's stable. The car is empty. It's got a ping pong table in it, and two people are playing ping pong. And you get out your measurement stick and you measure the speed of the ball, like back and forth. That's great. So they hit it at whatever 5 miles an hour, like back. If you could do that when the train was driving past you and you measured the speed of the ball, you get two different speeds. Because the ball going with the direction of the train will get the speed of the train plus the ball, and the white guy hitting it back will get the speed of the train less the ball. Right? But if you climbed onto the train with your measurements while they were playing, and you could be driving along, going along, and they're going back, but you'll get the regular meaning, the same reading you got from standing on the platform. That's what it means for time and space to be relative. The relative position of the observer. It's called his or her frame of reference. And this colors absolutely everything. So if you have questions wondering about what your subjective mind is doing, there's another layer of issues to add on top of that. Now, the points that follow, we're going to go through pretty quickly. Well, 8.2.2, 2.2, speed of light was the new absolute. What makes Einstein's work so revolutionary, what he showed that time and space were not absolute. Those had been standard absolutes of the Newtonian world. And but
Wait, say that again. I'm so sorry.
time and space were absolutes in Newton's world.
Okay.
And now they've been made relative in Einstein's world. And the only thing, but there is something which is absolute, and that's the speed of light. Right? So what Einstein was, he showed that the speed of light was absolute. 2.3, time is slowing down. If the speed of light is absolute, nothing can exceed that speed. So if something appears to do so, say the headlight on a moving train, so the train moving by at 100 miles an hour, and you turn on the light and it jumps out a certain distance and you measure it, it's going to be more than 186,000 miles. If you go to 100 miles an hour, it's going to be 186,000.05 miles or something like that, right? So if you took that and divided by 1, velocity is distance divided by time. It's like you drive 100 miles in 2 hours, you get 50 miles an hour, right? So distance, 186,000.05 divided by 1 gives you a speed of light of 186,000.05 miles per second. And that's not possible. Something's got to give, right? Speed of light can't give is 136,000 miles per second. The distance it traveled can't give because it did travel 186,000.05 miles. Time's got to give. As if time becomes, instead of 1 second, it becomes 0.99999999999 and divided into 186. You get 186,000 miles per second on the snoot, right? Believe it or not, the math is that simple. This has actually been demonstrated with well, this is not the one. Leave that alone, right? These are barely measurable until you get near to the speed of light. But time is slowed down. It's this famous time dilation, So you put two twins, you put one on the ground, you put one in a rocket ship, and they go up, they fly around the moon 20 times and come back down. The one who's been on the trip is a little bit younger. The one who's still. Yes, Dan.
So going back to your headlight train.
Yeah.
And so instead of the because the flight can't go any faster than 186,000, but the train is in fact going 100.
Right.
So instead of the headlight overheating, because the light is backing up in it at 100 miles an hour, what happens is you get to your destination a few seconds sooner in this demonstration.
Well, I guess you get to a destination. My point was that you can talk. I'm not saying you're not arguing. You can talk about these things all day long and get very confused in your head. In a second, the light has gone actually 136,000 plus a little bit because the train has moved it along. In that second, has moved it along a little bit more. And so the distance is real, but you're not allowed to calculate that as the speed of light. Right?
Okay.
Math gets more massive with speed. Mass to a physicist is resistance to force, not size or weight. So as matter moves faster, it gets increasingly resistant to any force applied to it until it reaches the infinite mass at the speed of light, which would need an infinite force to increase its speed. It's just that limit out there. You can't go faster. This has been shown in high-speed accelerators where the ability to further accelerate particles reaches a dead end. It just can't get go any faster. 2.5, mass energy conversion. If acceleration of a particle results to maximum speed, if that results in maximum speed, means that it has maximum mass and cannot have any more energy, then mass and energy, both max out at the same point. Perhaps mass and energy are the same thing, but Einstein demonstrated that was the case, hence we have E equals mc squared, energy mass times the speed of light squared. And I like to say that I think of the Big Bang as I tend to say the insertion suggests that there was some place that exists to insert it. It's just the creation of an infinite amount of energy. You didn't have to make any mass because that energy was something that was going to come together in mass, but as it began to cool down, and so forth, just that giant spark, boom, all the energy the universe would ever need.
The mass and energy are the same thing.
Yes, mathematically they're the same thing. Yes. Okay. Which brings us to general relativity. All of special relativity revolved around observers in uniform motion, but Einstein was troubled by one unanswered question. One, what happens when an object changes speed or direction? It seems there must be some outside force acting on it. To understand this, we need a definition or two. First, any change of speed or direction in physics is called acceleration. This is number 3, chapter 8, number 3. I know that's counterintuitive that slowing down would be considered acceleration, but it is something that results from the application of force, just as speeding up does. When a body has no external forces acting upon it, that is what physicists call inertia. This will usher in the difficult thought that if you were to drop a ball off a bridge, as it falls, it is not subject to any forces at all. But what happened to gravity, you might ask, and thereby hangs the tail of general relativity. As Einstein thought, Einstein determined there was no experiment that could be designed that could separate these two concepts and that they were in fact the same. In a rocket ship accelerating at 1g like Earth's gravity, right? You're standing on the floor of the rocket ship. You can't tell whether you're being pulled down to the floor or pushed up by the floor as it flies off into space. Right? So that your determination of whether you're experiencing one or the other is up here. Another thing gone to the subjective box. Right? This equivalence is important to our next point, 4.2, curvature and why light bends. If you rolled a ball across a rubber sheet that was attached to a frame, right, so it's taut, you rolled a marble across, and it would roll across in the direction you did, it's fine. Then take a slightly, like a billiard ball, something heavier, put it in the middle, so the whole sheet goes like that, and now you roll a ball on it. What's going to happen? The ball's going to be diverted in some way. If you get too close to the ball in the middle, it'll probably go in and crash into it. If you don't, it'll be turned into a curvature as it goes around. That's what's happening. Well, right? That mass is deforming space. There's a geometry to space. And anything that looks like it's being affected by gravity is actually just following the trajectory of the changes in space-time. And since light has mass, it too can be bent as it travels across this geometry. But when in a normal day, if you look at the stars, I mean, light just shows up. You can't tell whether it's done an S-bend or, what is it? It just shows up. But in 1919, they went out during an eclipse and they looked for a star that they knew would be very close to the sun, where normally they couldn't see its light. But when solar eclipse was on, they could see the light and they measured it, and the star looked like it was way off place. It's because the light was being bent as it passed close to the sun, and Einstein's general relativity was confirmed. So how is this relativity received? Is everything relative? The reception was almost universally positive. There were lots of reasons for that, but the exhaustion of the public from the Great War was certainly one. This was something to take your mind off that horrendous event. 5.1. But artists and poets picked up the theme. For example, some attributed the rise of cubism in art to relativity, attempting to show different perspectives of multiple observers on the same subject. When confronted by this, Einstein remarked that the person suggesting it had not understood my theory. Poets invented new meters for their poems that were much less rigid, and music, some claim discovered chance music, resulting from what is called the 12-tone row. Ask me later. But there were misunderstandings. 5.3.1, the general public interpreted relativity as support for the pessimism and relativism that permeated Western culture after the First World War. From the London Times in 1919, it is confidently believed by the greatest experts that enough has been done to overthrow the certainties of ages and to require a new philosophy that will sweep away nearly all that has been hitherto accepted as the axiomatic basis of physical thought. Einstein tried to push back against this, wanting to rename his theories invariance theories. But many of the traditional pegs of reality, time, space, velocity, have turned out to be dependent on the observer. This would seem to be the very definition of subjectivism and would appear now to include those former pegs of reality in with the qualia or secondary characteristics. 5.4.2, getting rid of absolute time and space proved highly unsettling both for science and the wider culture, but the aim was to preserve intact the laws of nature, specifically the laws of electromagnetism represented by the velocity of light. Take a bit of a breather. It seems from the history that we have covered so far that man, while it began making the journey as an integral part of early science, as things progressed, he seems to be increasingly marginalized up through the Enlightenment. God is forgotten, and we no longer had his guarantee of intellectual capabilities. We replaced him with mathematics as the guaranteed model of truth. Then that collapsed. Kant kindly allowed us to have our mental world, but strongly suggested it had little relationship with reality outside our minds. The Enlightenment tried to finish off Christianity, perhaps the most human of all relationships. And along comes Einstein in a funny sort of dual way, breaks down more of our certainties, but also thrusts us back into the fray as the observer. Everything seems to revolve around our position. It seems no wonder the modern world is seen as neurotic. But it will get worse as we look at the new field of quantum physics, but there's some good news on the horizon. How are we doing? We got 10 minutes. All right. Maybe I'll skip the biology one. Quantum mechanics. This chapter explores the challenges posed by quantum mechanics, the probabilistic and seemingly acausal nature of quantum events, which replace the strict determinism of classical physics, raise deep philosophical and metaphysical questions about reality. The authors explain the key concepts of quantum physics and the various interpretations that have been proposed to make sense of its mysteries, showing that even in modern science, philosophical and religious questions are unavoidable. I particularly like that last sentence because it is patently the case that there is, as yet, 100 years later, no consensus on how we should interpret quantum mechanics in human terms. None. Not none. But what is this all about? It's about the subatomic world, the parts that make up the atom. But in what's coming, don't expect explanations. We'll visit what quantum physicists have found, but frankly, no one really knows why the world appears the way it does at the subatomic level. 1.0, in short, the revolution in physics in the 20th century created a revolution in worldview, undermining the Newtonian paradigm that had reigned for nearly 3 centuries. Gone was the image of the universe as cold impersonal machine. Gone the image of humans as mere cogs in this mechanism. They hailed the new physics as the great emancipator. It seemed to open the door once again for free will and human dignity. Whether it did that or not depends on your point of view, or I dare say your metaphysical presuppositions. Let's look at the flip side. But the revolution had its disturbing side. Gone as well was the certainty of an objective order of the world. Gone was the confidence in the human ability to discover any coherent truth. British physicist John Gribben leads off an otherwise sober book about the new physics with a sweeping assertion, what quantum mechanics says about the world says is that nothing is real. Well, that is certainly bracing, right? So what is a quantum? It seems that most things that we measure have units of inexhaustibly varying size. Think miles down to feet, to inches, to microfeet, whatever, to little micrometers and so on, right? But energy, when we reach the smallest values, has a minimum level or smallest level called the quantum. So energy comes packaged like that. It's like you wanted money, all money can be divided by pennies. The pennies are kind of the quantum finance. So atoms absorb, it turns out that atoms swirl around the nucleus of the atoms, but each level of orbit is a quantum of energy different. And atoms absorb or give off energy by electrons moving up and down from orbit to orbit. One of the interesting things is sometimes one kind of physical bond that 2 atoms make is they share an electron in the outer orbit. So it's going around this way. That's really, really hard to break those. That's quantum. I could turn the page, would be great shape. For number 4, particle or wave. This is one of the most problematic ideas of quantum physics, which of course doesn't lack problematic ideas. Is light a wave or a stream of particles? Going back to experiments in the early 1800s, we saw photons behave like waves, and that when the waves interacted with each other, they produced a hybrid pattern. Think of a pond, you throw two rocks in, they both start a set of ripples going out, and then when they cross, you get that interference pattern like that. Well, light does that as well. Very much like it. It's a wave. But I've got this experiment here that says it's a particle, right? And so that we now have experiments where, depending on how you do them, you can get it to show wave or particle. And one of the things that's really weird, it can be showing wave, and then if you turn on a machine to observe it, it goes back to particle. Right? You'll see in your thing there, a YouTube thing. YouTube thing is about 9 minutes long. It will really, if you have any care for this thing, it's a very good explanation of this. Wonderful. Quantum entanglement. Did I put that in here? No, quantum entanglement. It's a phenomenon where two or more particles become linked in such a way that they share the same quantum state, no matter how far apart they are. It means if you measure one, you get the measurement of the other. If you change one, the other one changes. As far as we know, there's no limit on the distance, and it's instantaneous. Superposition. A particle can exist in two different states at the same time, called superposition. This is one of the points of the thought experiment known as Schrodinger's cat. We can take that up in Q&A if we have any time. The superposition and entanglement are both major features of what they're trying to build in the way of quantum computers. But then quantum wave function. Such seemingly incomprehensible findings force physicists to resort to a mathematical formalism for representing the probability of any particular state of a quantum system. This probability wasn't about some value we didn't know, but about something we could not know. In other words, probability was no longer a shorthand, but a core part of our description of the quantum world. At the very fundamental basis of reality. And yet the calculations made with these equations turned out to be accurate and reliable. But when we observe a system described by a quantum wave function, it is said to collapse and deliver only a single answer. But why should such an observation have that effect? Which raises the question of observer-created reality. There's several different positions. One is that people say, well, really, we just don't know enough and we'll figure this out someday. And it'll look just as mechanical and deterministic as every other part of the world. Physicists like Niels Bohr, on the other hand, viewed uncertainty as not as a result of temporary ignorance, but as a fundamental and unavoidable limitation on human knowledge. His longstanding Copenhagen interpretation of quantum behavior said properties of such systems are not defined until they're measured. Werner Heisenberg, famous for his uncertainty principle, even reached back to Aristotelian terminology, right? To reach back to 300 BC, right? And said that the transition from the possible to the actual, which is a very important thing in Aristotelian things, actual things have lots of limited, but lots of possibilities. An ice cube can be melted, it can be, whatever, but it can't be made to sing the Star Spangled Banner, things it won't do, He said that the transition from the possible to the actual takes place during the act of observation. Very unusual. Real Twilight Zone stuff. And finally, there's a many worlds position that all the quantum possibilities do indeed occur, just in different worlds or universes. Right? Remember whatever happened to Occam's razor, right? What all this is about as to what role mankind and mankind's brain plays in the world we know as reality, or even if it has a role at all. Remember back to our discussion of secondary characteristics or quality of taste, sound, shades of color, all of which had no place in the physical signals in which we appear to find them. A chord on a piano does not signal that it is major or minor, nor a mountain lake that it is beautiful. So if our brain manufactures these qualities, how can we say that they're part of reality? They deserve to form part of what we sometimes cavalierly call reality. Some very intelligent people seem to think so. But if nothing else, it does appear that the classic distinction between observer and observed seems to have collapsed. Mm-hmm. And that chapter ends with 9. It is perhaps more accurate to say that physics has merely recaptured its true nature. After all, though most of its history, physics has been deeply intertwined with questions of metaphysics. Historical figures such as Galileo, Descartes, Newton, and Leibniz offered their scientific theories within a context of philosophical and theological discussions. The new physics has merely brought us out of the temporary aberration of positivism that only science gives us any truth, right? It has returned science to the broader fabric of human knowledge. That strikes me as good advice. In honor of the clock, Biology is very interesting. An interesting story. But we thought we knew if we just learned how proteins were put together that we'd understand it well. Then we started figuring out a protein, and if it had 200 amino acids, then we knew 199 of them. We had no idea what the 200th one was, so there was nothing regular about it. There was no formula that you could make to build this thing. Right? There must be something somewhere. It turned out to be DNA, but DNA turned out to be a string of nucleotides which act like an alphabet. You know, I had no idea what they meant. It looked like a code, but we didn't know a code for what. And then we found out that was being read in a different part of the cell. We took them 3 at a time, and that made a code for amino acid. So you had 2 codes. And the question is, how could the message in DNA be created in the first place without knowledge of how those letters were going to be read? Right?
Wow.
It's impossible. Right? You can't invent a code and somebody else invents a decoder and expect them to work. Anyway, that's important. So I think we're gonna jump right to the end. You okay for another couple of minutes, 5 minutes?
Yeah.
Yeah, okay. Jeffrey received this. Jeffrey received this book half a year ago, the Spencer Clayton, and he stamped his name in it, and then gave it to me. Man knows what to do, right? It turns out that the forward in here is by Stephen Meyer. And Stephen Meyer is one of the top people in the intelligent design movement. He wrote Signature in the Cell, Darwin's Doubt, and a book called The Return of the God Hypothesis. These 3 really phenomenal works. Billy just saw a presentation made on that. I paid attention to those. I never did this one. It was just too geeky. He gets into quantum cosmology. I don't know. I don't know regular cosmology, right? But Spencer Clavin is a PhD in ancient Greek, but a very erudite and well-read and knowledgeable young man, still in his 30s or maybe he's 40. And he wrote this book, Light of the Mind, Light of the World, Illuminating Science Through Faith, right? And the cover inside it says, "The world is not a machine, humanity is not a mistake," right? And so he goes through the whole history of science and does a very good job of it. And in fact, a man who I have greatest respect for, not William Barr, that was the guy who was Attorney General, Stephen Barr, I think his name was, wrote a book called Modern Physics and Ancient Faith, which I absolutely adored. I gave it to a friend of mine who was exiting from financial services and training to be a Methodist minister in retirement down at Emory. And he loved it so much, he used to read it during his devotionals. Right? So really, really good. So Barr reviews this guy's book. I read the review, it's very good. And I saw a letter from Clavin, and this was in First Things. And the letter said, I can't help but be thankful to Barr. As Barr says, when he picked up a book on science written by a guy with a PhD in ancient Greek, he said, I was worried I could be treated for a lot of warmed over limp science. He said, I was totally wrong. Right? I've got a good stamp of approval. So it goes through this whole thing. But I want to read from Meyer's intro to this. The story Spencer tells me interests me deeply. In many ways, it parallels the story I tell in my own work, especially the God hypothesis. Like Spencer, I see the history of modern science as a rise, a fall, and a rise. The first, and you'll get this now, the first rise is the development of modern science within the Judeo-Christian tradition of Western Europe from the Middle Ages through the 6th, 17th century. That's through the Enlightenment, right? The fall is a decline of theistic science in the face of materialist theories that seem to explain our origin, our human nature, without recourse to a creator. This is exemplified by what Spencer has called the hyper-Newtonianism of characters like Pearcey, Laplace, and others we need not bear, who, unlike Newton himself, took Newton's mechanics as a replacement for God's agency in the universe. Indeed, I find Spencer's take on Newton, that his theology was integral to his science, a refreshing antidote to the secular trope that science and religion are necessarily in conflict. But by the time Newton published his work, the belief that human reason could completely replace religious belief was already being entrenched among the thinkers of the so-called Enlightenment. Already, many elite intellectuals saw no need to make recourse to theism to explain anything about the universe, past, present, or future. As Spencer explains, Newton's laws were seized on and divorced from the context in which, and indeed the foundation on which, Newton himself had presented. We talked about being stripped of his religious writings and set up as the absolute, the great mechanic. And so it was in the name of Newton, but not at all in his spirit, that the vision of a purely materialistic, mechanistic Newtonian universe came to be. You've been lied to, someone said, right? That's what a surprise. When Spencer interviewed me for his podcast, he asked me if there ever was, in fact, a period of time during which scientific atheism seemed like the most reasonable hypothesis. I think that late 19th century was such a time for elite intellectuals. Laplace seemed to have explained the origins of the solar system, Charles Lyell the origins of geological features, Darwin the origin of species, all without recourse to God. Even the problems of our human nature seemed to be explained by the materialist ideas of Marx and Freud. At least they did at that time. But I believe that despite the narrative of the new atheists and the media, the materialist zeitgeist, which has been on the wane, has been on the wane and will ultimately prove but a blip in the history of science. And that's because we're in the middle of another rise in the plot. My book, Return of the God Hypothesis. In my book, I detail 3 major scientific advances that made belief in God entirely reasonable for scientists and non-scientists alike. First, the discovery that the universe is not internal but had a beginning. Second, the discovery that we are living in a Goldilocks universe in which the fundamental physical laws and parameters are finely tuned for life. Many people say it looks like the universe expected us to come. And third, the discovery in molecular biology of an entire realm within each single cell of exquisite, intricately constructed molecular machines, information-based nanotechnology. Each of these discoveries speaks to the necessity for mind as a precondition for the existence of our universe. And then the relationship between mind and matter, the mind of God, the mind of man, and reality on the smallest scale is Spencer's central theme and the basis for the intriguing questions he asks about current theories of quantum physics and the consequent breakdown of the hyper-Newtonian materialistic worldview. Ready? Can matter exist apart from the mind of God? I talked to my PhD physics daughter, I mentioned this to her, and she said what I say. If you think the strong nuclear force is important, yes. No, it can't, right? Because we stay together only as long as God keeps the strong nuclear force in us. The people, what does it mean for the heavens to roll up like a scroll? Well, you take away the strong nuclear force, it'll roll up like something. What would the universe be apart from the mind and experience of man? Do we search in vain for meaning, or does our very experience of the universe as creatures in the image of our creator confer reality on the universe it could not otherwise possess? Are we painting it technicolor? Back to Howard. It's drab and flat. And we're seeing all the differences, right? Is science bringing us back to God and placing us with him at the center of all meaning? Scientists have convincingly that our universe was created, that it had a beginning. For Spencer, the next question is this: is it only with our participation that creation is complete? I rest my case. This book, Light of My Mind. Yeah, that was Stephen Meyer's forward.
Yeah, that's a great introduction.
Well, thank you for your patience.
Yeah.
Thank you.
Thank you. That must have taken several minutes to put that presentation together.
I used to be 78, now I'm 82. That's not time dilation, that's time expansion. My life is going faster.
I'll say, okay, so here's the question. What's the summa? What is the soul of science?
Metaphysics, soul of science, because it is intimately involved with the human person. And human persons are only really complete if they have some kind of metaphysical position on the world. It doesn't have to be mine or yours or somebody else's, but they need to have in some way confronted these issues and thought about them. And if you want to draw from science to help you understand what reality looks like and what it is, that's fine. And I don't have any problem with someone being a methodological materialist. That's fine. But don't do that and come back and tell me that you can't find God. Philosopher Edward Fraser liked to say, you go out on the beach with your metal detector, you go around for a couple hours, you come back. He says, did you find any wooden things? No, there weren't no wooden things buried out there. What do you like excuse me, using metal detecting. Right? And so, and one of the things I've come across, like the scientists are in this funny position that they can really only study, they can't necessarily study what they want to study. They can only study what they can study. That means, is the data available that they need? Are the machines available to gather the data that they need? They may have a great idea, but if you can't gather data or you can't find it or whatever, you can't study it. And you often look, your hypothesis about the world helps you frame the kinds of questions you ask. That's a very easy. Here's a piece of data that supports me. Here's a piece that doesn't. Here's a piece of data that supports me. Otherwise, it doesn't support me. We don't need that one. I tell you what, we all fool ourselves. I would say man is not man is the rational animal. He's really the rationalizing. So can we trust our minds? The only thing that's going to underwrite our trust is God. We tried Euclidean geometry, we tried set theory, we tried axiomatic method, we tried all these things. We can't get around the fact that every one of us is using our mind, and our mind seems to be a big player in this whole thing. Can't wipe it out.
All right, very good. Thank you. Well, next week is our final week, and we're going to, because we've covered several books, I think about 8 or so, and they are so substantive. I thought next week we would have 10-minute reviews on the major theme in each book, from Viktor Frankl, his Man's Search for Meaning, to the Soul of Science. And so anyway, very much looking forward to that. There is a reality in the TMI idea, too much information. And so a lot of these books, again, are just so substantive. And so I thought it would be very, very beneficial, instead of doing one more book next week, if we just go back and emphasize the major points of the ones we've covered. So I think you'll find that to be practical and helpful. So good being with you. Those of you joining us online, great to see you as always.
Thank you.
So we'll let you know about all that. I'll send out an email in the next 2 or 3 days. Again, looking forward to wrapping up the course. And Bruce, thank you for your presentation this evening. So good to see you all. Have a good evening. Good
everybody.
week. Great to see you all online as well. Thank you.
Bye.
Bye-bye.
Thank you.